Okay, one more quick video here. This is going to be on Lewis structures and how to make a decision about some different situations with Lewis structures using something called formal charge. Let's say you had the Lewis structure for our first example. Atom here is going to be NO2. N contributes 5 valence electrons. Oxygen contributes 2 times 6. Or 12 valence electrons. The total here is 17 valence electrons. What that means then, when I go ahead and draw the structure, I'll put N in the middle and I'll put an O on each side. I'll octet both atoms. And then I can count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So here I have 20 electrons. I need to get down to 17. So the first thing we know to do here is to make a double bond. We erase those 4. I'll make a double bond to the right. I could have made the double bond to the left. It doesn't make any difference. That gets me down to 18 electrons. I need to get down to 17, which means in this structure somewhere, I have to remove an electron. But the question becomes, what electron do I remove? The most sort of mindless answer would be to say, well, nitrogen's the guy with the odd number of electrons in the first place. Shouldn't I remove one of his? And we might find out that that's true. But there is a better way to predict which atom is most likely to lose the electron in this case. Let's pause with this Lewis structure right here. We're just going to leave them alone. We're going to come back. We're going to learn what this formal charge thing is, and then we'll come back up and decide which of these electrons we would remove to get down to our 17. Formal charge is the effective nuclear charge. That's the unshielded protons, or the amount of charge in the nucleus when you consider all of the inner protons and you cancel out the inner electrons. For example, with a atom like lithium, it would have 3 protons. I don't really care about neutrons for the sake of formal charge. 2 electrons in the first shell and 1 electron in the next shell. The formal charge takes the 2 inner electrons and the 3 protons and cancels them all out and treats them as one inner charge of +1. That was +3 from the protons, -2 from the electrons, or +1. If you think about that then, the effective nuclear charge is always actually going to be equal to the number of valence electrons for a neutral atom. So, if I consider the periodic table, and again, we're going to ignore the transition metals for right now, although the transition metals, well, we can talk about that when I'm back, but it's a fairly straightforward pattern for them in formal charge as well. Or, sorry, not a formal charge, but effective nuclear charge is going to count across just like valence electrons does. The effective nuclear charge in this category would be +1, +2, +3, 4, 5, oops, I need another category, 6, 7, +8. So, we start with the effective nuclear charge. Let's go back up to our example. Nitrogen is in the 5th column of the periodic table, ignoring the transition metals, so he's a +5. Oxygen is in the 6th column, so it's a +6. Next, we consider the lone pair electrons that each atom has. So here, again, coming back up to our example, I'm just going to give myself a little space to work with here. This oxygen atom has an effective nuclear charge of +6 and -4, 1, 2, 3, 4 unshielded electrons. So it has an effective nuclear charge, or it has, so far it's at +6 -4. This nitrogen has +5 minus this lone pair 2. And this oxygen would have plus 6 minus 2, 4, 6 minus 6 electrons from these unpaired. Last, each atom gets to contribute 1 electron from any bond that it's a part of. So this oxygen atom, what happened there? This is where we are. Sorry. This oxygen atom has 2, 4, but it's also a part of 2 bonds. So if we give it 1 electron from each one of these bonds, then that would be minus 2. So its formal charge right now is 0. This nitrogen has plus 5, minus 2 from these lone pair electrons, and then 1 from each of these bonds, minus 1, minus 2, minus 3. So its formal charge right now is 0. This oxygen, on the other hand, plus 6 from its effective nuclear charge, minus 2, 4, 6 from its lone electron pairs. Remember, he gets 1 from that bond, and so his formal charge is minus 1. Okay, so that's how you calculate a formal charge. How does that apply to what we need to make, what decision we need to make in a Lewis structure? Well, to get the best Lewis structure possible, the formal charge on each atom should be as low as possible. So let's go back up here and look at this. Low doesn't necessarily mean more negative. What I really mean here is closer to 0. So this atom is actually really happy right now. His formal charge is 0. This atom is really happy. His formal charge is 0. But this atom, his formal charge is minus 1. What that means is, effectively, in its region, it has a little bit more negative than positive. It's a little unstable that way. So if I just take out one of the electrons here, if we recall, our initial problem was that we were at 18 and we need to go down to 17. Now as a molecule as a whole, we're down to 17. And I lose one of these electrons associated with the unpaired electrons, and the formal charge of the molecule goes to 0. So the electron that needed to go away, or the electron that would disappear to make the formal charge work, was this one here that was part of one of those lone pairs. Again, I thought initially when I looked at this structure, and actually as a student the first time I did this, that since nitrogen is the one that contributes the odd number of electrons, it's going to be the one that has the unbonded pair. If I look at the formal charge of the overall molecule, I see that it's the oxygen atom that is the one that's going to lose its 1 electron in this situation. That's how we use formal charge to attempt to come up with the right Lewis structure in a complex situation.